Every day, the world produces roughly 5.8 to 6.3 million metric tons of municipal solid waste. Around 1 million tons of that is paper and cardboard. More than 700,000 tons is plastic, roughly 300,000 tons is glass, and about 240,000 tons is metal. Together, those four categories add up to more than 2 million tons every single day. Each has a different use and a different value. Yet once these materials leave homes and businesses, they rarely remain in four neat piles. They are crushed, broken, mixed together, and contaminated with food, plastic bags, wires, clothing, and other items that were never supposed to enter the recycling system. A modern recycling plant may receive tens of tons of this mixed material every hour. The conveyor belts cannot stop while workers inspect every item. So the system has only a few seconds, or sometimes a fraction of a second, to decide where each object should go. How does a plant separate paper, plastic, glass, and metal quickly enough to keep the line moving? What allows the machines to identify the material in front of them? And once the sorting process is finished, how much of it is actually ready to return to manufacturing? The process begins when a recycling truck enters the facility. The vehicle is weighed, then driven into a large tipping hall where its entire load is emptied onto the floor. What comes out rarely resembles the clean bottles and cardboard boxes that residents placed in their bins. The material has already been compressed inside the truck, shaken during transport, and pushed into a dense pile. A front-end loader moves that pile toward the beginning of the sorting line, where a metered conveyor breaks it apart and spreads it into a more even layer. This first step matters because no sensor can identify a plastic bottle hidden beneath a sheet of cardboard, and no mechanical screen works properly when dozens of objects arrive as one tangled mass. Before the plant tries to recover valuable material, workers usually remove the objects most likely to damage the equipment. This is not detailed sorting. The workers are looking for large plastic bags, hoses, electrical cables, clothing, pieces of wood, scrap metal, and anything else that could jam the machinery. Flexible plastic is especially troublesome because it wraps around rotating shafts and discs, gradually building up until the equipment has to be stopped and cleaned by hand. A lightweight shopping bag may appear harmless, but inside a sorting plant it can cause lost production time, damage bearings, and place workers close to machinery while they cut the material away. Lithium-ion batteries create a more serious risk. When a battery is crushed by collection equipment or punctured on a conveyor, it can short-circuit and ignite among paper, cardboard, and plastic. The U.S. Environmental Protection Agency found more than 240 lithium-ion battery fires reported at 64 waste facilities between 2013 and 2020, and advises that batteries and devices containing them should be taken to separate electronics or hazardous waste collection points, rather than placed in ordinary household recycling. Once the largest contaminants have been removed, the plant begins separating the material by using differences that are easy for machines to detect. It does not start by trying to identify the exact chemical composition of every object. It first separates things by size and shape. Large cardboard boxes are wide and flat, while bottles and cans are smaller and tend to roll. Many facilities use rotating disc screens that allow flat cardboard to travel across the top, while smaller containers and broken glass fall through the gaps. Other plants use ballistic separators, which shake materials across an inclined surface so that flat, lightweight objects move in one direction, while rigid three-dimensional containers roll in another. The exact arrangement differs from plant to plant, but the basic purpose is the same: turn one complicated stream into several simpler ones. This early separation determines how well the rest of the plant will perform. If paper continues to cover plastic bottles, optical sensors cannot see the bottles. If broken glass remains mixed with paper, the fibers may be too contaminated for a paper mill to accept. Screens and air systems continue separating lighter, flatter paper from heavier containers. cardboard, and mixed paper, then move toward quality control stations, where workers or robotic systems remove plastic film, glass, and other material that followed the paper onto the wrong belt. Paper also loses value when it becomes wet, greasy, or heavily contaminated. A clean cardboard box can be pulped and used again, but a box soaked with food or covered in wax and plastic may no longer meet the requirements of the mill buying the material. A recycling plant is not simply trying to produce a pile that looks like paper. It is trying to produce a commodity with a predictable level of moisture, fiber quality, and contamination. After most of the paper has been removed, the remaining stream contains a larger concentration of bottles, jars, cans, and broken glass. Steel is one of the easiest materials to recover because it reacts strongly to a magnetic field. An overhead magnet or magnetic drum pulls steel food cans, bottle caps, and other ferrous objects away from the conveyor. The machine does not need a camera to recognize a soup, can, or read a label. If the object contains enough iron, the magnet can remove it directly from a stream. Aluminum requires a different method because an aluminum can is not attracted to an ordinary magnet. Instead, recycling plants use an eddy current separator. Inside the machine, a rapidly changing magnetic field induces electrical currents in conductive non-ferrous metals. Those currents create their own magnetic field, producing a force that pushes the metal away from the machine. As material leaves the end of the conveyor, aluminum is thrown farther forward into a separate collection area, while glass and plastic follow a shorter path and fall into another chute. Steel is pulled away by magnetic attraction. Aluminum is separated by electromagnetic repulsion. Plastic is considerably more difficult. Two bottles may have almost the same shape and color while being made from different polymers. Soft drink bottles are commonly made from PET, while many milk and detergent bottles use HDPE. Food containers, lids, and other packaging may be made from polypropylene or several other plastics. These polymers melt and behave differently, so mixing too much of one plastic into another can reduce the strength, appearance, and value of the recycled material. To identify them, many modern plants use optical sorters equipped with near-infrared sensors. Material is spread into a thin layer and carried beneath the scanner at high speed. Different polymers absorb and reflect near-infrared light in different ways, creating a spectral signature that allows the equipment to distinguish PET from polyethylene, polypropylene, paper, and other materials. Once the system identifies a target object, software calculates its position and movement along the belt. A row of compressed air valves opens at exactly the right moment, blowing that bottle or container into a different chute. To someone watching the belt, the object appears to change direction instantly, but the machine has already scanned, classified, located, and ejected it. Optical sorting has clear limitations. A large label can hide part of a bottle. Leftover liquid adds weight and contamination, and some dark plastics remain difficult for certain sensors to identify. Packaging made from several materials presents an even larger problem. A drink carton may contain paper fiber, plastic layers, and aluminum bonded together. The machine may identify the package correctly, but that does not mean the layers can be separated economically. The triangular recycling symbol printed on a package also does not guarantee that every local program can process it. A material is only useful to a recycling plant when the plant can separate it in sufficient quantity and when a downstream buyer is prepared to purchase it. Glass often leaves the mainstream earlier in the process. In many facilities, glass breaker screens crush bottles and jars and allow the smaller pieces to fall through openings beneath the conveyor. The glass then passes through additional screens, magnets, air systems, and sometimes optical equipment to remove caps, labels, metals, stones, ceramics, and pieces of plastic. Ordinary bottle glass can be cleaned, crushed into cullet, and returned to a furnace, but ceramics and heat-resistant glass behave differently when heated. Even a small amount of the wrong material can create weak points, stones, bubbles, or other defects in a new glass container. By the time the material reaches the end of the sorting line, the original mixed load has become several separate streams: cardboard, mixed paper, steel, aluminum, glass, PET plastic, HDP plastic, and sometimes additional grades of plastic. Final inspection stations remove objects missed by the equipment. Some facilities still rely heavily on workers for this stage, while others use robotic arms and camera systems to recognize and pick contaminants. Machines provide speed and consistency, but people remain useful when an object is folded, damaged, partly hidden, or unlike anything the software was trained to recognize. Each recovered material falls into a storage bunker until enough has accumulated for baling. Sorting, however, is not the same as recycling. At this point, the plant has produced marketable raw material, not a new product. Paper must be mixed with water and broken into pulp, then cleaned to remove ink, adhesives, plastic film, and unusable fibers. Steel and aluminum must be shredded, cleaned, and melted. Plastic bottles are washed, ground into flakes, and processed into pellets or other feedstock. Glass cullet receives further cleaning before it is blended with raw ingredients and returned to a furnace. Only after these materials enter a new manufacturing process and become another box, bottle, can, or product has the recycling loop actually been completed. The purity of each sorted stream determines whether anyone will buy it. This means the plant is not merely separating material into different piles. It is repeatedly improving the purity of each material until it meets the specifications of the next factory. Reaching that level of purity is expensive. In 2024, WM spent nearly $39 million upgrading a recycling facility in Wisconsin, raising its potential processing capacity to as much as 70 tons per hour. Across the United States, modernizing recycling collection and processing infrastructure would require billions of dollars in new investment. Even with advanced equipment, some material will still be lost. Small fragments fall through screens. Contaminated paper may no longer have usable fibers, and multi-layer packaging can cost more to separate than the recovered material is worth. Other materials may be sorted correctly, but still have no reliable buyer. Putting something in a recycling bin, therefore, does not mean it has already been recycled. The plant only separates discarded objects into cleaner raw materials. Paper, plastic, glass, and metal must still be transported, processed, and accepted by a manufacturer before they can return as new boxes, bottles, jars, or cans. The recycling plant is an essential part of that system, but it cannot complete the process on its own. Thank you for watching. If this video changed the way you see a recycling bin, please like the video and subscribe to the channel for more explanations of the hidden systems behind the things we use every day. See you in the next video.